Hi everyone. Okay, so in this session, I'm going to continue our lecture on a topic form. Okay, so in the previous lecture, we have discussed on the example one and the introduction of this topic. Okay, so without further ado, let's restart. Okay, so in these examples, you can see that we have frames with slanting column and the beam. Okay, so this particular frame is imposed by the point load at point D and the UDL load in lateral direction. Okay, so based on these examples, so we will see how the frame structures can be analyzed based on the a few things that you not ever deal with before. Okay, uh, as usual, you need to calculate the reaction at support. Okay, so by considering the three equilibrium equation. Okay, so by looking on the frame structures, you can see that we should to have three numbers of cut section. So where two at the member CB. So where you can see that before the point load 40 kilonewton and after the point load of 40 kilonewton, you need to have cut sections. Okay, so and one numbers of a cut section along AC. Okay, so by considering the three equilibrium equation, you can see that the reaction at support B is equal to 103 kilonewton, VA is equal to 63 kilonewton, and HA, which is a horizontal reaction at support A, is equal to 173.025 kilonewton. Okay, so I don't want to focus in detail on the reaction at support, so I hope that you can figure out by yourself. So I would like to concentrate on the beam analysis and means the member analysis on these frame structures. Okay, so okay, this is the slanting member in the frame structures. So what you need to do for this particular step, what you can see in this slide is you need to convert the UDL load into means that you need to change this particular UDL load into UDL that imposed along a member AC. So what you can see here is this particular UDL is not perpendicular to this particular member. So you need to change this UDL so that the UDLs becomes perpendicular and parallel. So the process is explained in this slide. Okay, so let's relook on this diagram. So the first thing that you need to do is you need to convert this UDL into point load. So by multiplying the 20 kilonewtons per meter with the height of this frame, which is from A to C. So the height of this frame can be obtained by using this angle of 60 degree by using the trigonometry. So this height is equal to, if I'm not mistaken, is equal to 8.66 meter. Okay, so 8.66 meter. Okay, so by multiplying the UDL with the 8.66 meter, the height of this frame, so you get that the point load is 173.205 kilonewton, which is acting at the mid of this member. Okay, so the next is you need to convert this particular point load into a component, the vertical component and the horizontal component. In other words, you need to convert this point load into a component that in a local axis direction of this member. So what you can see, the global axis for this frame is this is vertical. Okay, so this is a vertical global axis, and this is horizontal global axis. Okay, so now we will focus on the local axis of the member. So the local axis of this member is this way. So this is a vertical local axis, this horizontal local axis. So what you need to do at this stage, you need to convert this point load into a component that in a local axis. Okay, so due to that, you can get the vertical component of this local axis for this member is by multiplying the point load with the sine 60. So we'll get this vertical load that perpendicular to this particular member. And by multiplying this point load with the cos 60, so you will get the horizontal component which is parallel to this member. Okay, so you need to bear in mind that this load actually is a UDL load. Okay, so what you have converted here is a point load, so you need to convert this point load to become UDL load. Okay, so by dividing this point load that you have converted into a local axis of this member, so by 10 meter, actually this length of a member is a 10 meter. So by using this 60 degree, by using the trigonometry based on this 60 degree angle, so you will find that the length of this member is 10 meter. So meaning that to get this UDL of 15 kilonewton per meter, so you can divide this value of 173.205 sin 60 divided by 10 meter. Okay, so you get the 15 kilonewton per meter, which is a UDL that perpendicular to this slanting member. Okay, so and when you're dividing this value of 173.205 cos 60, which is the horizontal component that parallel to this member, with a 10 meter, so you will get the UDL of 8.66 kilonewton per meter, which is acting along this member. Okay, so the next step, you can get the equation of moment, shear force, and axial force for each cut section. Okay, so this I think the new thing for you that you have learned in this slide, where you didn't learn in the previous the previous means that during the diploma, if I'm not mistaken, this not included in your syllabus. Okay, so I hope that you can figure out how to convert the UDLs into a local axis. So basically, this is a global axis. Okay, so this is a first cut section, which is along a member BC. The range is 0 to 3 meters, which is on this member. So on this range of from B to the point load. So the cut section, the first cut section considered is here. Okay, so by taking a moment, okay, so the x is measured from the support. Okay, so this x, by taking a moment about the cut section, so you can see that the moment is equal to 103x. Okay, so and by considering the summation of force in the vertical, so you will get the equation of a shear force, which is here the equation is equal to 103 kilonewton. And by considering the summation of force in the horizontal, you will get the equation of axial force. But here the axial force value is a 0 kilonewton. Okay, so basically the axial force doesn't give a significant effect on the horizontal member. Okay, that's why you have found that in the beam analysis, the axial force doesn't important in the beam analysis, but in the frame analysis, when the member in a slanting, the axial force will exist. Okay, so we look later on the other member. Okay, so let's we move on the member BC, which is the range is 3 to 5 meter. So basically the range is around here. Okay, so from the point load towards the joint C. So this is the free body diagram. So the x remain the same. We measure the x from the support B. Okay, so by taking a moment about the cut section, so you can see that the equation of moment is given by this equation, which is a 63x plus 120. Okay, so by considering the summation of force in a vertical, so you will get the equation of shear force, which is equal to 63 kilonewton. So you can cross-check this equation of a shear force by differentiate this equation of moment, where 63x differentiate this 63x, you will get the 63 value. Differentiate this 1 to 0, so become 0. So and based on these solutions, we have seen that we got the correct equation of shear force and bending moment. Okay, so and in a horizontal direction, so you will get the equation of axial force, and again you can see that the axial shear force for this member is equal to 0, as what we have seen in the previous cut section. Okay, so let's we move on the last cut section, which is along member AC. The range is 0 to 10 meter. Okay, so we have converted this UDL load into a local axis in the previous slide. Okay, so in this slide we will get the equation of moment, shear force, and axial force. So let's start with the binding moment equation. Okay, so by taking moment at the cut section where the x is measured from the support A. Okay, so is it correct? The support A. So yeah, this is a support A. Okay, so this is internal moment mx. So we have UDL load which is 15 kilonewton per meter, and this UDLs along the beam. Okay, but here this particular UDL doesn't affect on the equation of bending moment, because principally the bending is force multiplied by the distance. So there is no distance in between this UDL towards the cut section point. Okay, so the only forces that we need to consider here is four numbers, or means that four numbers, which is this 15 Newton per meter, the reaction at support, two numbers of reaction at support, and including this internal moment. Okay, so and simplify all this equation, you can see that the equation of moment for this member is equal to 118.50x minus 7.5x squared. So one thing that you need to figure out here is the distance between these reactions towards the cut section. For instance, here you can see that 173.21 multiplied by 0.866x. Okay, so basically 0.866x is a perpendicular distance from this horizontal reaction at support A towards this cut section. Okay, so and for the 63 kilonewton reactions, the perpendicular distance is a 0.5x, which is from this point towards this cut section, the horizontal distance, which is a 0.5x. So you need to identify this relationship. Okay, when the x is moved, I mean that when the x is moved from point A to the cut section, so you need to get the corresponding vertical and horizontal distance for the 63 and the 173.205 kilonewton distance. So I hope that you can figure out this by yourself. Okay, so and by considering the summation force in these directions, which is I can say that this is a vertical direction of local axis for this member. So and by that you will get the equation of a shear force. So you can see that in this direction you have a 173.205 sine 60, which is come from this member. Okay, so you need to convert this fraction. I mean that from the direction you need to convert into a vertical. So you get the component, and also for this vertical directions you need to convert this into component, and this will opposite from the our positive signs conversion. Okay, so and this UDL, so multiply with the x distance, you get the total load. Okay, so I simplify this, you get the shear force equation for the member. Okay, so for the axial force, you can see that you need to consider all the loads in this direction of x, which is in this local axis. Okay, so in this direction you need to have this particular 8.66 kilonewton per meter UDL that acting along the member, and you need to get the component of this reaction at support 173 and 63 that you need to resolve into this direction. Okay, so simplify this, you can see that the equation of the axial force for this member is equal to 141.162 minus with 8.66x. Okay, so we have obtained all the equation of a moment, shear force, and axial force for every section. Okay, so and you can proceed to draw the shear force and the bending moment and axial force for the member. For instance, here in this slide shows the shear force diagram for beam, and this is a shear force diagram for the slanting member or slanting column. So in the total, you can see that this is a shear force diagram for the frame structures. And this slide shows the bending moment diagram for the frame. Okay, so and this okay, so that's it for this sessions. I think I hope that you can figure out what we have learned in this session, and we will continue in the next session for the example 3. Okay, so that's it. Thank you for listening.